Im Namen der GmbH heiße ich Sie sehr herzlich willkommen zu einer weiteren Veranstaltung unserer Experten-Webinarreihe mit dem Titel Neues Siliziumkarbid LinPak steigert die Effizienz von Hochleistungsanwendungen. Die Fachpräsentation heute hält Herr Virgilio Botan. Herr Botan ist der BIMOS Product Manager bei der ABB Power Grid Semiconductors aus Lenzburg in der Schweiz. Mein Name ist Ralf Jessler und ich bin bei der GmbH für das Business Development zuständig. Nun möchte ich aber gerne die Gelegenheit nutzen und meine Firma, die GmbH Leistungselektronik, kurz vorstellen. Diese Darstellung fasst unsere wesentlichen Kompetenzen und unser Angebot zusammen. Ich denke, die meisten der heutigen Teilnehmer kennen uns als Distributor von leistungselektronischen Komponenten. Allerdings legen wir Wert darauf, dass wir über die reine Vertriebstätigkeit hinaus unsere Kunden während des gesamten Produktlebenszyklus unterstützen. Neben den typischen Aufgaben der Distributionslogistik bieten wir Ihnen bei Bedarf zudem gerne ingenieurfachliche Unterstützung unserer Experten an. Neben der Ware unserer Handelspartner haben wir eigene Produkte im Programm, wie komplette Umrichterstacks oder hochisolierende Stromversorgung. Über die Distribution hinaus engineeren und fertigen wir bei der GmbH Baugruppen und Systemen nach Kundenvorgaben, üblicherweise im Bereich von ungefähr 100 Kilowatt bis Megawatt pro Endstufe. Diese Folie zeigt unser Vertriebsportfolio, das sich wie folgt zusammensetzt: Treiberschaltung von Power Integrations aus der Schweiz, Leistungshalbleiter von Hitachi ABB, ebenfalls aus der Schweiz, Proton Elektrotechs aus Russland und Fuji Electric aus Japan, zudem hochwertige Luft- und Flüssigkeitskühler von Mecal aus Italien. Wärmeleitfolien haben wir auch im Programm für die Leistungselektronik von Neograph aus Ohio, Vereinigte Staaten. Neu im Programm haben wir Leistungs- und Hochspannungswiderstände von EBG aus der Steiermark, Österreich. Und bereits seit vielen Jahren vertreiben wir Strom- und Spannungssensoren von Petersem aus Frankreich und Kondensatoren von Elektronikon aus dem ostthüringischen Ort Gera sowie von der noch weiter östlich gelegenen Firma Yanghai aus China. Wie bereits erwähnt, bieten wir zudem eigene Lösungen an, wie Plug-and-Play-Treiberkarten für Thyristor und IGBT, die wir gerne auch in kundenspezifischen Entwicklungen einsetzen. Dann haben wir hochisolierende Stromversorgung, GPSS und IPSS im Programm, entwickelt für die potentialgetrennte Versorgung von Baugruppen auf unterschiedlichen elektrischen Potentialen, sowie unser modulares Umrichtersystem Varis, das in verschiedenen Stromrichtertopologien und Kühlarten erhältlich ist. Sollten Sie Interesse an unserem Varis haben, kann ich Ihnen einen interessanten Artikel von meinem Kollegen Herrn Erik Rehmann empfehlen, der im März letzten Jahres in der Fachzeitschrift Elektronikpraxis erschienen ist. Was uns von den üblichen Distributoren unterscheidet, sind unsere Fähigkeiten und Aktivitäten im Bereich der Entwicklung von leistungselektronischen Baugruppen und kompletten Systemen sowie Engineering-Dienstleistungen. Als exemplarisches Beispiel ist hier ein Prüfstand dargestellt, der eingesetzt wird für Stoßstromtests von Schutzeinrichtungen, die in batterieelektrischen Antrieben eingesetzt werden. Die Stoßstromquelle liefert bis zu 35 Kiloampere bei Spannungen in Höhe von 1500 Volt. Dank IGBT-Technik sind Einzel- oder Mehrpulstests bei typischen Pulslängen von 5 Millisekunden möglich. Wie das Bild zeigt, haben wir dazu eine gewaltige Kondensatorbank aufgebaut mit einer Gesamtkapazität in Höhe von sage und schreibe 2 Farad. Diese Anlage wurde gleich in 2 Artikeln der Fachzeitschrift Boros Power Systems beschrieben. Der erste ist von uns und ein weiterer von unserem Kunden. Hier noch ein kurzer Blick auf unser Entwicklungs- und Engineering-Team mit unserem Entwicklungsleiter Herrn Soldan sowie ein Prüfsystem für Mittelspannungstransformatoren. Selbstverständlich fertigen wir auch leistungselektronische Baugruppen oder Systeme, sehr flexibel in Bezug auf die Stückzahlen, angefangen von einem oder mehreren Prototypen bis zu einer Serienfertigung von einigen tausend Stück pro Jahr. Gerne zeigen wir natürlich auch einen Auszug unserer werter Kunden. Sollte Ihre Firma noch nicht dargestellt sein, naja, dann denken Sie doch bitte bei Ihrem nächsten Projekt an uns. Zu guter Letzt noch der Hinweis auf unsere Präsenz bei LinkedIn. Wir würden uns sehr freuen, wenn Sie uns auch hier folgen. Stellen Sie sicher, dass Sie stets über Neuigkeiten, über unsere Lieferanten und Aktivitäten auf dem Laufenden bleiben. Den Link zu unserer Seite finden Sie beispielsweise am Ende jeder Mitteilung, die Sie von uns erhalten. Damit bin ich auch schon am Ende mit meiner Kurzpräsentation und leite gleich weiter zu Herrn Botan nach Lenzburg. Hallo Herr Botan, sind Sie bereit?
Yes, it's besser.
Okay.
Okay, so I wanted to give a bit of insight about the LinPak of silicon carbide and what we are doing in Hitachi ABB power semiconductors to improve these modules, this semiconductor, the capability. So they give really advantages in different applications. So starting with this, how do we judge how good a semiconductor is? So we one of the key parameters is we look at the technology curve. The technology curve is the let's say the relationship between switching losses and on-state losses, and with these losses we have a technology curve, and we can move on this technology curve. We can optimize different semiconductors for different applications. For instance, for an MMC, where usually the switching frequency is relatively low because of the multiple cells that they switch, is an advantage to have a device that is optimized for low on-state, even though the switching losses are a little bit higher because of the low switching frequencies. It gives an overall benefit. Or on the other side, if we have a two-level system where there's only two switches per phase, it tends to switch at higher switching frequency. Then we look at devices that are rather optimized for switching losses. They have lower switching losses, even though we have to pay a little bit of price in on-state losses. And when we manage to improve both of them in the same time, then we talk about moving the technology curve in the green curve on the left side. And this is then an improvement or a second generation improvement of these devices. Now, if we look at these different devices on different points on the technology curve in a different dimension, namely in output current versus frequency, we see that different devices have different characteristics. So a slow device will have higher output current, the light gray curve, a higher output current at lower switching frequencies, but then lower output current towards the higher switching frequencies. And if we manage to move the whole technology curve to the green curve above, then we have more output current over the whole frequency range. You can see that at higher switching frequencies, the usual silicon device or IGBT devices that we have nowadays, all the devices, the output current decreases with increasing switching frequency, no matter how they are optimized. And this is the area where we see the development of wide bandgap modules or semiconductors. Now, looking at this curve, output current versus frequency, here I just wanted to give a short, let's say, evolution in history in the late years, how the technology has developed. And you can see in the graph on the right-hand side, different output curves, current versus frequency of the different technologies. So starting with normal planar technology, we call them, our brand name is SPT, soft punch-through devices. Then we have the generation of SPT plus, SPT plus, where we improved the plasma on the emitter side. We increased the plasma level on the front side. Then moving to to combining this enhancement layer or the SPT plus technology with a trench for an enhanced trench, and then even more advanced chip technologies like the BiGT, the bidirectional IGBT. With all this different technology and different steps we do in development, we always manage to increase the current density. So for the same, in the end, for the same module that you can buy from us, you can get more current out of it by decreasing losses, by improving thermal, and so forth. Now, if we look what we have done in the last let's say last half a year to a year, we looked at even more advanced trench designs. And if you know the concept, one has a gate trench which you can pack more emitter side on one side, increase the current density. But these trenches are usually, because they go very deep into the device, they are very sensitive to, especially at high hard turn off events. They are very sensitive to hot charge, to very energetic carriers. These energetic carriers can penetrate, can enter into the oxide at the bottom of the trench, because we have very high electric fields. We have a lot of charge into the device, and in time deposit their charge, or in time destroying the gate oxide, which of course in turn has negative influence or changes the switching of the semiconductor. So what we do as a first measure, we add to this active trench a so-called dummy trench. Dummy trench is physically a trench exactly like the active one, but is not connected to the gate potential, but to the emitter potential. And this has the role of screening the electric field near the bottom of the active trench, in this way protecting the bottom of the active trench from dynamic avalanche, for harmful charges that can penetrate there. And even further than improvement or protection of this is going with on the right hand side with a P top region even deeper, as a further measure to improve the plasma flow and the charge around the active trench, a further protection method. And we do a lot of simulation. We analyze these different designs and techniques, and then we also test them. And in the next, you can see on the technology curve, E off versus on state, we realized also with different anodes and different thickness of device, the design number 3 at different points on the technology curve. And then we go into switching, and these are nominal switching. This is single chip switching, turn on events. And we also do then also repetitive tests. So we go in a very hard dynamic avalanche when we go in multiples of nominal current, in this case 4 times the nominal current. Also we increase the voltage as much as possible, so we create very, very harsh conditions for the chip in order to stress it as much as possible. And we do this repetitively. You see here after up to 100,000 cycles of this switching, and we look at DIDT if the turn-on event keeps its characteristics after all this let's say very harsh switching events. And this is for us a measure that we take in order to see the stability of these devices, of new technologies. Yeah. Now going on the packages. So this is, we look at what we do generally at the chip, looking at the packages, the LinPak. LinPak is the first package that corresponds to roll to rail, to the European initiative in trying to establish a standard for silicon, but also for silicon carbide devices, especially for traction, but then can be extended this standard also to industrial application. It has a lot of benefits. It has a very low strain inductance. The physical characteristic with the separation of DC plus minus potential and the AC. In the end, compared with the standard, we call them HiPAC or IHM modules, we have a much better, a much compactor solution with much lower over voltages because of the strain inductance, and a much higher current density that one can achieve with this type of package. And you can see here also in paralleling up to 4 parallel devices turned on at also again very hard conditions with more than 10 kiloamp per microsecond, very hard turn on. You see the dynamic current sharing is almost perfect, and such devices are not let's say matched for parallel connection, but they are taking out of production. So the package itself was optimized. Of course, we started with silicon. This runs since several years, and because of the benefits of this package, is also, of course, very suitable for silicon carbide. We are also developing on the high voltage the similar package, going from 3.3 to 6.5 kilovolt. And here I show exactly the same procedure that we have for the low voltage, with protecting the device also in the fabrication to have error-free devices. We have here our air blade that we do during the ultrasonic welding of terminals in order to eliminate all the particles from the device. And all these technologies we apply for high voltage, but also for low voltage LinPaks, in order to make robust as possible module. And here also for a 6.5 LinPak switching curves, in which we see very nice switching, SOA conditions, 2 times nominal, very clean switching. And now if we go to the main topic of this, it's silicon carbide. So we saw how much we invest in this, in the packaging of this device. And this device is, to our knowledge, the first one where we optimize it for silicon and silicon carbide in the same time. So due to its very, very low internal strain inductance in the range of 10 nanohenry, we can very well make use of this package to put silicon carbide inside. And you see a little bit here the design of the substrate, where in case of silicon, we have this area filled with, I have to see if I find where I have my tracker pointer. Can you see my pointer? Maybe Herr Jetzes, can you see it? Let's go on. For the silicon, we have the area filled with silicon chips, and in silicon carbide, we have this extra structures there for a better distribution of the emitter or source signal and the gate signal, to have an homogeneous possible switching of these small devices. And as we remember from the beginning, we had this output current versus switching frequencies. And in the case of silicon, we have this drop at higher switching frequencies. And now for silicon carbide is the first material where we have a chance to improve the output characteristic or output current at high switching frequencies. And you see on the right-hand side, the reason for that is the silicon carbide, as I think we know it, has very low switching losses. And of course, one can optimize and one can see what are the compromises also in making the device switching faster or slower. And I'll come back to that in the next slides. Now we saw the package. Coming back to the chip itself. We work a lot on the silicon carbide MOSFETs themselves. So we look the characteristics. Of course, the main key feature is RDS(on), and we look at this how we can improve the on-state characteristic of this device. And you can see here in the schematic, the RDS(on) has different parts going from the emitter channel, the JFET area, the substrate, the drift, and each of them have their own characteristics and dependencies. And we investigate a lot the channel resistance, and also, of course, how we can optimize the other one, like the substrate and JFET area and drift and so forth. And here in the right-hand side graph, you see next to the silicon carbide unipolar limit, what devices with the red triangles are out there or published by us or different competitors for different voltage classes, the 1.2, 3.3, and even 6.5 kilovolt. We see the higher the voltage class we approach this unipolar limit, but also for the lower voltage class, there's different techniques by optimizing the channel, optimizing the substrate to get as close as possible to the theoretical limit of these devices. And I will now skip this slide for lack of more time. We developed a high K technology where we look at the dielectric of the oxide and compare it with the standard silicon oxide that we have in most of the silicon carbide devices. And instead of the silicon oxide, we'd use a material with high K. And you can see on the left graph, in terms of on-state characteristics, in the first quadrant, so in the channel conduction, we see between 30 and 40% improvement for this high K with the same thickness of the high K material versus silicon oxide. And also in the third quadrant, where we have the freewheeling diode operation, either the unipolar, the conduction with the channel, or the bipolar conduction of the diode, the body diode. For both of them, we see improvement of the high K material versus standard silicon oxide. And on the right graph, you see a similar comparison of the RDS(on) versus in a temperature range, where we can see consistently for the same pitch, for the same the electric thickness on the gate, we have a better performance for the high K material versus the standard silicon oxide. So then a further optimization that one does is looking at the geometric characteristics, looking how we can optimize the pitch, how we can optimize the channel length to get the lowest losses. And here we can see in this graph on the right hand side different pitch distances for the cells, how the characteristics are. So there's an optimum around 13, 14 micrometer, and then it goes up again if we go lower. And this have effects of different parts of the RDS(on), like the JFET with reducing pitch is always increasing. The channel is decreasing. And at some point, the optimization of the compromise of these different effects plays the dominant role. But this is what we are looking at, different designs. Where do we find the sweet spot for such designs? By the way, this is a 3.3 kilovolt design where we have this, let's say, specific RDS(ons). And here in a comparison on the left graph, we have different influences. We have the pitch as we saw it in the previous graph, but we have also the channel length, and we see that both with the pitch and channel length playing with these values, one can further and further improve the RDS(on) or the specific resistance. But we see that in case of the high K, we have the lowest RDS(on), even if we have a channel length that is 250 compared to the lowest one, 150 for the silicon oxide case. And on the right graph, we have the leakage current, and here also we are searching for different designs to offer us the lowest leakage. Again, comparison of different channel length and silicon oxide versus high K material. And we see that with high K, because we can have different electric field that goes deep into the semiconductor, we have different leakage current, and the interface density is of course for high K material different than in the case of silicon oxide. Coming back to the switching characteristic, we see with this high K material turn-on event, a very hard turn-on event with very high DIDT, and it's very clean. We don't have oscillations, also turn-off waveforms, and in the right-hand side curve also RBSOA. And here you see the current per centimeter squared going up to 200. And if you think that in a LinPak we can pack roughly 10 square centimeter of such semiconductor, you can imagine the power of these devices. So one advantage of the high K is definitely the RDS(on), an improvement in on state. But second, equally important, could be even more important, characteristic of the high K material is their stability. Here we see turn-on events where we sweep from minus 15 volt to plus 15 volt on the gate to source signal, and what we see also out there from competition and also otherwise, we see that these materials, the gate is very sensitive to high negative voltage bias. So in a lot of the devices, you will see a very asymmetric gate potential, in the negative going only down to minus 10 or even sometimes only minus 5 or minus 6 volt. And this is due to the fact that at higher voltages, negative bias, this gate oxide can get damaged. But we prove with our material and our design that we go really in repetitive, very hard or very high negative bias on the gate, as we are used to in the silicon, minus 15 to plus 15, and you can see turn on events even after 11,000 pulses of this hard switching. We have the characteristics, they are overlapping on each other. So no degradation whatsoever. And this, you can see it also more quantitatively on the right-hand side graph, where we monitor from the turn-on events the threshold voltage, and we see that we have a very stable along all these switching events, a very stable characteristic or threshold voltage. And also these devices, they are very rugged. And here we do short circuit events, and depending on different pitches and of the cells and different optimization of the channel, we have more short circuit current or less, and we optimize it in a different way, rather for on-state or for short circuit. But you can see we have also devices that survive quite a long short circuit, and otherwise we have also designs that also heavily exceed this number. And also here, if one looks at the short circuit energy, when compared the silicon oxide gate electric with high K material, we see that the high K has a big advantage. So as a summary, we see for the high K that we improve the channel. We improve the channel conduction by reducing the resistance there, heavily improve the gate stability, and also this material is very rugged. And now if we look on the module side, what we discussed a little bit in the beginning, depending on the gate driving condition, one can go from very aggressive switching with very low RGs, going to for this 3.3 device to 1 ohm, 1 point something ohm, or even more aggressive, going towards 0 external RG, or to higher in order to get smoother characteristics, and of course also for the turn off less oscillation. So it's always the game to be played in different configuration, in different converter designs where different L sigma are present, to find the optimum between switching losses and controllability and behavior of shapes of the switching curves. We also are looking a lot at high voltage silicon carbide, and by high voltage I mean even higher than 3.3. You see here for 6.5 kilovolt devices, we compare them, the MOSFETs versus the IGBT technology. So what would the different, because the higher the voltage, one sets the question which technology it would be better, an IGBT or MOSFET. We have the dependence of the RDS(on) versus temperature, and also looking at the third quadrant, how we can operate either the channel or the diode in this. So we are looking and comparing a lot versus the existing silicon choice, silicon IGBT choice, and see where the sweet spots are for this technology. And here some switching events where we see that this is also nicely switching. We still have some oscillations. We work to see on which switching parameters are the best for this technology, but we are intensively looking at this technology. And for me, it was especially impressive let's say the SOA, the ruggedness of such chip, even at 6.5 a silicon carbide MOSFET, we could switch these devices at 3 times nominal and at voltages up to 5 kilovolt. And we were actually, in this case, limited by the tester and not by the device itself. So extreme ruggedness for such chips. So we are very excited to see how we further develop this technology and launch it as a product. All in all, as a short summary, we have these packages. We have different for the substrates, different way of populating with silicon carbide. We have the so-called single population, or double, where we put double the amount of silicon carbide inside for, of course, for higher current rating or for lower RDS(on). We have seen that we get much lower switching losses as expected compared to the silicon variant, and this can be also further optimized by, depending on the topology and what around this semiconductor is, by using different RGs, different way of triggering these devices. In conclusion, we have for the LinPak, both in silicon carbide but also in silicon, we have voltages 1200 volt to 6.5, 1200 volt in the near future, currents from 300, of course, for 6.5 up to almost 2 kiloampere. And then we have in different isolation voltage, and we see a lot of applications that can very well make use of these devices. We see already the first demonstrators and the first series of either traction converters, especially 3.3 or 1700 volt, but also other types of application like StatComs or battery charges or solid state transformers and so forth. So if you have any questions or need more information, please contact us, contact GVA, and we'll be happy to help. Thank you for listening, and thank you for the attention.
Okay, thank you very much indeed, Mr. Botan, for this really interesting presentation about the Hitachi ABB LinPak equipped with silicon carbide MOSFET chips. Then let's start with the Q&A session. Sie, liebe Teilnehmer, stellen Ihre Fragen bitte in Deutsch oder Englisch. Beides sollte funktionieren. Vielleicht, wenn Sie noch einen Moment brauchen, kann ich die erste Frage stellen. Ich stelle sie auf Englisch, wenn es in Ordnung geht. So what is, Mr. Botan, what is the commercial situation in terms of prices of silicon versus silicon carbide today and the evolution in the coming years?
Ja, ich habe gerade überlegt, soll ich Deutsch?
Aber ich kann die Frage auch gerne auf Deutsch stellen. Also,
nein,
okay.
Also wir wissen, dass die Siliziumkarbid-Modulen sehr teuer ist. Und der Hintergrund dafür sind die sehr teuren Chips, sehr teure Siliziumkarbid-Chips, die wir verwenden. Und das hat auch mit den Ausbeute und die Defectivity, die wir auf diese Substraten haben. Aber was wir in den letzten Jahren gesehen haben, ist wirklich eine massive Verbesserung in Kosten von diesen Substraten, in der Herstellbarkeit. Man sieht es Nachrichten, auch die Substratlieferanten, sie gehen mit Economy of Scales von 4 Zoll auf 6 Zoll und von 6 Zoll auf 8 Zoll gibt es Ankündigungen, und die Prozesse werden immer verbessert und die Ausbeute auch dementsprechend. Und wir sehen eben in den letzten Jahren, und ich denke, das wird auch in der nächsten Zukunft weiter so gehen, eine starke Preiserosion. Und wir kommen in einen Bereich, dass wir sehen, dass die Vorteile von Siliziumkarbid eben überwiegend sind gegen den höheren Kosten, dass man für so ein Modul immer noch hat und wahrscheinlich auch in den nächsten Jahren haben werden. Also die Vorteile werden auf dem Umrichter oder an die Applikationebene, wenn man über Traktion denkt, auf dem Zug, die Steigerung der Effizienz wird ziemlich schnell in Betrieb amortisiert. Ja.
Okay, vielen Dank dafür. Ein Herr Johannes Gloning fragt auf Englisch: Are there LinPak modules 1200 volts, 1200 amps for use in commercial vehicles available or in planning, silicon or and silicon carbide?
I mentioned in the end, I have this 1200 volts still as a bit in a different color. We from Hitachi ABB Power Grids, we offer right now the starting voltage class is 1700 volt. But we have on our roadmap or in development strategy to offer also 1200 volt, both with silicon and silicon carbide. But this will come in the next years. So we don't have now in the offering. If there's in application, because I remember this was the question already existing. This I cannot know if there's a system that use 1200 volt LinPak or LinPak equivalent modules in different application. I do not know, but I think this module has a very high versatility. And again, you can have in two variants this module from 1200 to 6.5, and the modularity and scalability with the parallel driving these modules offers a lot of possibility for modularization in a lot of applications.
Okay, vielen Dank. Dann fragt unser Marketingmanager Erik Rehmann: Hat die heutige kritische Chip-Verfügbarkeit am Weltmarkt auch Auswirkungen auf Hitachi ABB in Bezug auf Verfügbarkeit und Lieferzeiten? Und gibt es dabei Unterschiede zwischen Siliziumkarbid und Silizium?
Ja, also man hört überall, vor allem in den Medien, dass es die Halbleiter für Autoindustrie oder so eine sehr knappe Lage auf der Welt ist. Im Moment, wir spüren diese große Nachfrage oder die größere Nachfrage auch in den tieferen Leistungsbereich. Dort Module, die sie in Low Voltage Drives oder Low Voltage Wind-Applikationen Anwendung finden, die dort die Nachfrage sehr stark ist, und wir spüren dort ein bisschen Lieferprobleme. Wenn man an den Hochleistungsmodule denkt, wie LinPak oder HiPak, die größere Module, höhere Spannungsklasse, dort, ich denke, die Situation ist nicht so angespannt wie bei den Tiefleistungsmodulen. Und ob es zwischen Silizium und Siliziumkarbid hier einen Unterschied gibt, ich denke, der Unterschied geht eher in den Spannungsklasse, wie gesagt, die tiefere Leistung sind im Moment, oder wir spüren dort eine größere Nachfrage.
Okay, liebe Teilnehmer, stellen Sie Ihre Fragen. Vielleicht noch eine Frage von meiner Seite. Haben Sie das LinPak mit Siliziumkarbid schon mal, also mit Siliziumkarbid MOSFETs schon eingesetzt, schon im Einsatz irgendwo? Ja. Bei sich oder bei Kunden?
Also wir haben die Siliziumkarbid LinPak 1700 Volt 3.3er bei einer oder anderen von unseren Kunden in Demonstratoren drin. es gibt zu meinem Wissen keine, die als kommerzielle Flotte läuft, aber Demonstratoren sind schon in Einsatz. Ja. Und das hat bis dahin, ich denke, auch mit den höheren Kosten von dieser Technologie zu tun. Aber wie gesagt, jetzt sehen wir in den letzten Jahren eine ständige Verbesserung Preiserosion oder Kostenerosion. Und das wird sicher ermöglicht, dass mehr und mehr Anwendungen von dieser Technologie Nutzung machen können.
Ja, Sie haben ja weitere Gehäuse im Programm. Wir haben ja letzte Woche das Roadpack kennengelernt, Ihr Roadpack, ja, denke ich mal, das Gehäuse für E-Mobility-Anwendungen. Gibt es weitere Gehäuse bei Ihnen im Einsatz für Siliziumkarbid-MOSFETs und wofür steht genau das LinPak?
Ja. Also wir überlegen auch Erweiterung von den Plattformen in Modulen oder in Gehäusen, wie Sie sagen, neben den Roadpack, die schon jetzt für Automotive zur Verfügung steht und LinPak eher für größere Leistung Applikationen, wie ich hier geschrieben habe. Aber das werden wir in der richtigen Zeit noch erkündigen, ja, was die nächsten Gehäuse oder die nächsten Richtungen bei uns sind. Ja.
Okay, dann sehe ich gerade, es gibt keine weiteren Fragen. Sie können, liebe Teilnehmer, natürlich Ihre Fragen auch im Anschluss stellen. Kontaktieren Sie gerne mich oder unseren Vertrieb. Es gibt keine weiteren Kommentare. Ich denke, dann können wir das Webinar hiermit beenden. Vielen herzlichen Dank nochmal an Sie, Herr Botan. Und liebe Teilnehmer, vielen Dank für Ihr Interesse und hoffentlich bis nächste Woche oder bis zu einem unserer nächsten Webinare. Dankeschön.
Danke Ihnen. Schönen Tag.